Hello everyone and welcome to another APCS video. This video is going to be kind of a marking point where we transition from coding it or learning code in a way that's just control of a program, the movement, the basic actions or procedures that we might do. So we've learned how to store data, how to represent data with data types and variables, to do basic manipulations in terms of strings, in terms of arithmetic and math and numerical values. We talked about conditional statements, so this allows our programs to make branching decisions based on data, and this expanded our abilities quite a bit. And the last topic we discussed was iteration, the ability to loop and repeat code in a compact way. And so those are all great tools to make things happen, but real pieces of software that grow in complexity, the kind of stuff we're used to in big programs, whether it's Microsoft Windows or if we're on a Mac, an iPhone, all the apps that we use, everything that we do, they're way more complex, and mainly because they abstract from very specific technical things like just doing arithmetic to bigger picture situations. And so we need to have the ability to kind of abstract away some details, and even though the details must exist, we wanted to talk about our data, our functionality in broad abstract concepts. And this is something that we do as human beings really, really well. And so the goal is to try to, can we do this in our programming language, and if we can, what will it do for us in terms of the complexity of our programs? And so near the beginning of the year, we talked about this idea of object-oriented design or object-oriented programming, and the Java language in particular was designed with this idea in mind. And essentially what it boils down to is that we will describe information, things, often real-world objects that we want to mimic in our computer systems, but not always. We want to describe their data, the content of what they are, and their functionality, and then we can write code that represents them and use that to make complex decisions and control information and manipulate information. And this is a little bit different from what we've been kind of doing, which is considered procedural. We're saying take this first step, take the second step, do this third thing, and so on. And this is a good approach, but it is limited in terms of how we can control data. And as it gets more complex, we run into this problem of how can we change it, can we be flexible, and that becomes really difficult to manage. And so object-oriented design is going to take the idea that something that we do instinctually and expand it to our code. And so when we talk about things in the real world, for example, if I asked you to describe what a chair is, it's a pretty broad question. It may seem silly, but if I asked 3 different people what a chair is and you had to give a definition, that might not be as easy as we might think. Right? Most people say a chair is something you sit in. Sure, but does that tell you what a chair looks like? What is its shape? What material is it made out of? Does it have particular features that other things do not have? And so just the question of what a thing is can be a challenge, and that's maybe a philosophical issue, but it does boil down to, can we give specific details? And for a computer system, the same problem occurs. What is the thing we're trying to describe, and what information could we keep track of, and what functionalities might we want to represent this thing? And so in Java, the way we're going to be doing this is we're going to be using classes. And we've already seen this class keyword, and we may have used them, but we're going to take it further and say, well, instead of just putting a main method, which is where all the programs kind of started, and just writing individual lines of things, we're going to write classes in a way that instead of being data or things happening, they're more descriptors of data and functionality, and then at some point we will use those to make things happen. And again, this idea is abstraction, and this is a hard concept, and initially it may seem like, why are we doing all this extra work? And that's a pretty reasonable question to ask. But we'll see that long term, the benefits kind of outweigh the little bit of extra work the programmer has to do. So when it comes to classes, we're going to categorize them into 3 different sections. And we've already seen basically 2 of them. The third one is the newer one that we're going to be discussing. So I'm going to say that I'm going to write some notes here. We'll say there are 3 types of classes. And excuse my handwriting is not flawless. 3 types of classes. And the first one that we've seen, again, is very much just a functional thing. And we'll call this a main class. And this is typically a class that its main purpose is to have a main method, just the starting point of the program. So all the ones that we've done so far have been pretty much main classes. Classes that they have a main method and they do something. They have some action that occurs. And so that's as simple as it gets. And every program will have a main class somewhere along the line because that is the beginning of a Java program. But they're pretty simple in what their intent is. It's to make the beginning of the program begin and take off from there. The second category of classes that we've also seen is what we might call a utility class. And again, to be a utility class, what we're saying is this is a class that has some subset of functionality that's related to one another. And the example that we've seen is the math class, right? The math is not a thing. I mean, I know the idea of math is a thing, but it's not like an object. It doesn't represent a real-world object, whether physical or not. It's the idea. It's a category of functions that might exist, and they're related to each other. So, you know, trigonometry is a form of math, and absolute value is an event that happens in math, and the square root and so on. And so utility classes usually are bundled functionalities that are related and helpful that programmers might want to use. But on their own, they don't represent any one particular thing, right? And some utility classes also have extra information. It's not always the case, but for example, the math class has the pi value and the e value, because pi and e are useful in mathematics. And there might be other ones in other utility classes, and there are many different things that we've seen. The third category, which is the new one, we've actually used two of them, and what we're really going to be learning from this point forward is how to make our own, and this is kind of a very powerful technique. And so what we're going to do is we're going to say the third category we're going to call data classes. Right? Data classes, or a data class, what it represents is a class that it's kind of like, what is a thing? What are we trying to represent? And often we want to represent real-world scenarios or real-world objects. And so as a kind of a good example, I think, if you think about how a video game is made, often video games are supposed to simulate some portion of real life. So a racing game might simulate what a car looks like, and a car has wheels, and a car has a functionality of acceleration and braking and turning. Cars have colors because they're paint jobs. They have weights because depending on how heavy they are, they might move slower. They have acceleration rates. They have horsepower. All kinds of information of what a car is. The racetrack is a physical ground. There's physical simulation. There's physics going on. And so we could describe what a car is by talking about, well, what data do all cars have in common? What attributes do all cars have in common? And then what functionalities do all cars have in common? And there's kind of an endless supply of the ways that we can represent all that information. But we could write a class or almost a blueprint to describe what this thing is, and then use it in our code somewhere. And again, the end goal is to connect data and functionality under one label. Right? We've kind of done some of this stuff already. We've made variables, and that's data, and we've done functionalities on those variables, and that's also perfectly reasonable. But if we want to grow our program, so for example, if we have a game that has 20 different types of cars, are we going to make just 20 loose variables for horsepowers or colors? What happens if there are 1,000 different types of cars, right? There's a huge number of cars, and so if our game is supposed to represent this, or if we're representing people, characters in the game, right? They have different heights, they have different speeds, they have different strengths, they have different, clothes, and clothes itself is another object. There's kind of an endless supply of things in the real world that we might want to mimic. And there's also sometimes ideas that are more abstract that we might want to also represent. And so relationships can also be interpreted as kind of a thing. So for example, the connection between a student in a grade book or a set of grades, that in itself could be like, what is a grade, right? A grade is not some physical thing. There's no physical piece of paper. It's a number. It has a meaning to us as people. We say, oh, this is a representation of the understanding of material that a student might have learned. But how could we represent a grade as part of a computer system? And we see that we know often it has to do with numbers, right? You have a 95, that's a type of grade. A grade point average is the average or summation in some particular scale of grades. And all of those things might need to be represented in a computer system. And so classes that are data classes are often meant to describe these things while tying data and functionality together. And the benefit, and the key that we're going to try to take away from all this is the benefit is that it becomes easier to manage and grow a program if we do that intentionally and with a little bit of kind of planning. So the next thing I want to kind of discuss, and so this is kind of a very vague idea. We're not going to put any code really in this video. We'll move on to another video shortly that has some examples. But I want to say kind of the general outline of what a class will have. And so I really, the classic example, and if you watch the AP videos that are available online, or if you read about it, other things from books or online resources, the most common example or analogy you're going to think of or hear when talking about classes is the idea of a blueprint. Imagine if we were contractors that need to build a house. Before we can build the house, we must describe what the house is going to look like. And a blueprint is typically a digital or hand-drawn document. The classic is this blue paper with measurements for all the sizes of the walls and where the doors are and where the windows are and which way the doors swing and how much width and what materials are made out of things and if there are stairs or multiple parts. But when you have a blueprint, you don't really have a house. You have the plan for a house. What is the content of the house? And so it's a little bit hard to describe functionality, but maybe the functionality would be like where the doors swing, where they open, where the electrical wires are, where the plumbing pipes are, and things like that. That's the plan. But until we actually construct a house with physical materials, we don't really ever have a house. We have a plan for one. And so classes are going to be like the plan of a thing that's going to be in our system. Right? But until we actually get some RAM memory locations and put values in some variables, we don't really have these things. So we might describe what a car is or what a person in a game is, but until we actually construct them, we're going to do that. And so there's different components when we make these blueprints. And so that's what I'm going to describe now is what are the common components of these class blueprints. And then when we do our example, we'll do 2 steps. We'll make our own blueprint to represent something, and then we'll actually create in RAM. And again, we say create, but it's not physical. It's more of like, hey, can you find some RAM and represent this data and keep it active in our system while the program's running. But to make this effective, we must kind of plan out a blueprint. And so we're going to talk about the kind of common features of a blueprint. So that's what I'm going to do briefly on the right side here. So a class has these features. Well, I cancel features. There you go. The first thing we're going to say every class has is attributes, and I'm going to put the word attributes, but that's not the proper terminology we're going to use. We'll talk more about the terminology that's specific to Java in a little bit. Right? So the attributes, or you must all call it data. So what is the information we're keeping track of? And so that's one portion, and that's always an important portion. And it is also very difficult to manage because for any concept, we might come up with hundreds of different pieces of information that we might want to keep track of. And we have to kind of tailor it and do the bare minimum to make it work, but not overdo it, and not also underrepresent the functionality or data that we might want. We also need the ability to make one of these things, to ask for the space in RAM. And so in Java, we're going to call these constructors, but these are like the builder of this thing. So like if we have the blueprint, can we make one of these blueprints come to life? And in Java, we're going to call these constructors, right? So we're going to say that we need to have some kind of constructor. Typically, we have one or more. We have the ability to make as many as we like, and the user of our class will use the constructor to make one of these things and then apply it in some fashion. And then the last category of information or things that we're going to need is the functionality associated with this data. And so typically we'll have methods, and then we're going to kind of split methods into 2 categories. So methods we know are basically things that can be done. Methods can be called, and their functionality, their code that runs when we call them. And we're going to split them initially into 2 categories, though these categorizations are still pretty vague on purpose. The first is what we'll call accessors. Methods that give us information from the class. So if we're representing a car, and a car has, for example, a horsepower that tells us how powerful the car might be, an accessor method may give us back that information. How much horsepower does a particular car have, right? Or the color, or the turning radius of the wheels as we turn, or a number of pieces of information. But these are methods and the reason that we might why would you say, well, we need a method if we have the variables themselves? And the answer is often we might have to do complex calculations or limit how we represent the data or show the data to the user and not necessarily give them direct control, but do some adjustment, right? Maybe the turning radius is based on the type of tire you have. And so if someone asks a car for the turning radius, maybe you have to do some mathematics to figure out what exactly it would be based on a particular type of tire that the car has. And it could change because they might change the tires. And so accessors are a way of gaining data in a meaningful way from our blueprint or from our classes. And the second category we're going to say is what are called mutators. And then hopefully we know the word mutate means to change. And so mutators are essentially a category of methods that change values, right? Again, in our example of a car could have its color change, right? You can recoat a car with a new colored paint, or a glossy coat, or a pearlescent coat. Or you might change an engine part and make the car more powerful, right? Or you might change the material of the seating. Some cars might have leather seats, some might have cloth seats, and those things may have the ability to be changed. And so a mutator is going to be a method that its purpose is to change content or data within one of these class objects or things that exist in this category. And so I'm going to stop the video here, and I know this is pretty vague, and again, the whole problem is that we are talking about abstract ideas, and so as an example, we need to kind of see something in code to hopefully make it more clear. And we'll talk about more specifically keywords and things that must be written in Java, because this idea applies to pretty much any programming language. But we'll go ahead and go from here at this point. Our next video will have an example. We're gonna go for something very specific, and it'll be funny because it's not going to be a car or an object that has a physical representation. Even though that might seem easier, that's actually kind of hard, because since we're kind of doing it in a very limited system and environment, we don't want to overdo it and try to simulate the real world perfectly. That becomes very, very challenging. So our example will be a little bit more simplified, but still pretty relevant and I think understandable. So I'll see you in the next video, and we'll keep going with our classes and go from there.